Hi, welcome to our deep learning final project demonstration video. This is Zijun from Team 7. Our topic is concept distance metric ensembling on state-of-the-art NLP models. So I'm going to start with our problem statement. As we have learned in class, transformers are the SOTA NLP models as of today. They usually achieve such high scores from fine-tuning the model with respect to specific tasks. We hope to combine the strengths of multiple NLP models with completely different architecture. So we're hoping to use ensembling techniques to create a more well-rounded model. We also notice a lack of research in ensembling of sentence embedding models, and therefore we have chosen to assemble several models that includes word embeddings. Those are GloVe, BERT, and LSTM. Regarding task, our baseline model used common word embedding ensembling techniques, including concatenating the word embeddings from different models, and then we used bagel boards to generate sentence embeddings. The NLP datasets we used to evaluate our model are listed as shown in the slide. We have used library CentEval for evaluation, and then sentence transformer for generating BERT embeddings, LNLP for generating LSTM embeddings. As you can see from the flowchart on the right, our baseline implementation is simply the concatenation of the word embeddings from Distill Roberta from the sentence transformer library and then GloVe embeddings. There is no training involved in the baseline implementation. And because the baseline does not show significant improvement than our original models, we have come up with two ways to further improve the performance. To improve our baseline model, we have proposed two solutions. The first one is to try adding a linear layer after the concatenated models, and then fine-tune the parameters by each individual tasks. The two models we have chosen are GloVe and the LSTM. The second solution is to try further concatenating the LSTM embeddings to the output from the baseline model. Similarly, there is no training involved in this solution as well. In this slide, I'm hoping to demonstrate to you the results of our experimentation. As you can see from the table, we have divided our data into 4 sections, where the first one is from the original GloVe paper, the second one is for our baseline implementations, and the third one and fourth one are for our improvement strategy 1 and 2. Feel free to pause the video if you would like to look at the data more closely. Our conclusion is the best model we have achieved is LSTM concatenated with GloVe, and then with a fine-tuned linear layer appended. We think it outperforms every other baseline models in every typical classification tests. Just for extra information, the shape of the linear layer has a width of half the size of input length, dropout rate 0.2, and the activation function is ReLU. In conclusion, our fine-tuned ensembled model with GloVe and LSTM has shown better performance in almost every task. We believe that concatenating embeddings from different models combines more features into one embedding. When comparing with individual models, this provides more space for the model to be fine-tuned. Our research could be used to further improve state-of-the-art models score on any natural language processing tasks. Some future work that we can think of are in the future, we can further increase the breadth of our research by introducing more models to concatenate. If time permits, we can even use voting strategy on classification tasks. Lastly, because we have seen large improvements with training just a shallow network, which is one linear layer, we're excited to see the results if we implement more complex networks after the concatenated results.